Hi, Cynthia.
Hi, Jonathan. Okay, I guess we'll get right into it. I'll keep the intro short because Jonathan wanted to keep it a little bit mysterious and open for the Q&A session afterwards. So welcome everyone to the fifth presentation of the Rising Tide Symposium, As Above, So Below. Today we are very lucky to have Jonathan Tennenbaum doing a presentation on the stupidity of artificial intelligence. Jonathan has a PhD in mathematics and works as a researcher and consultant on economics, science, and technology. He has written extensively on fundamental problems in the natural sciences, and most recently authored a provocative series of articles on artificial intelligence for Asia Times. He is also a classical pianist and lecturer. So with that, I will give the floor to Jonathan. Welcome.
Thanks, Cynthia. Thanks much. Well, I'm going to improvise a little bit. I had planned to think a lot more about the topic, but I had a deadline and just finished not very long ago, about an hour ago or 2 hours ago, a long series of articles about Joe Biden's climate policy. So now I've got to somehow get from there to intelligence. So anyway, also a very interesting topic. But artificial intelligence is a very, very big topic. And so I'm going to raise some issues and then hope that we can go into some of them in the discussion. In the series of articles, it's somewhat, I tried to approach it in a systematic way. The series is not finished. Actually, it's probably about a third finished. It has, I don't know, maybe 15 parts up to now. And as I worked on this topic, I began to discover more and more and realize how many very important questions about our world today, about ourselves and so forth, are bound up with artificial intelligence, particularly the way the discussion and also the implementation of artificial intelligence, but all the philosophical discussion that's been going on goes way back, of course. The way that affects almost everything and gives an occasion, that's what I think is most important, an occasion for us and for people to reflect upon what the human mind is. So I could formulate it in the following way, that by understanding the stupidity of artificial intelligence, we might become more intelligent. In the series I started, one of the first things I worked on was to try to get a good definition of what stupidity is. There are some books written about it. I'll take that up, not now, but at the end. The first thing, I want to get at this in the simplest possible terms because the subject is very complicated. Should try to reduce things to the essentials. I've grown up with this topic in a certain way because my father was a protege of Kurt Gödel, who was a very famous mathematician who did some fundamental work on the issue of, let's say, the transcendency of the human mind relative to any machine. I can make that maybe more precise in the discussion. That's very relevant here. So let's try first to demystify artificial intelligence. What is artificial intelligence? Well, concretely, it's just computers, digital computers, with programs. So it's computers plus mathematics. Essentially, there's really no difference between ordinary computer you use, and artificial intelligence, the main difference is the program that's being used. The program is essentially, essentially mathematics. This is very important because what we call artificial intelligence or an artificial intelligence system is something created by an intelligence, the mathematician or the programmer, who designed the program. And then you have this machine that carries it out. So now that sounds now a bit magical. How are you sure, or what's the reason for believing that there's more intelligence coming out than the programmer or the mathematician put into it? In fact, an enormous amount of human creativity and thought has gone into artificial intelligence. So I think that's very important to bear in mind, because people get it a bit mystified about the apparent magic of certain things which artificial intelligence systems do, which are very useful. It's certainly a very useful technology, also in a certain way a dangerous one, not in and of itself, but in the way people interact with it. So, first point is the concept of an algorithm, to get to really the essence of what a computer is, and a very big issue. Algorithm, intuitively, is some kind of procedure that you follow step by step according to some collection of rules, the rules being fixed. A calculational algorithm. And there's a thesis which is really not at all intuitive, or actually not at all obvious, and I think is wrong, which says that the human mind, or let's say the human brain, functions algorithmically. In other words, for example, if you're thinking about something, you are actually proceeding according to a series of steps, or your brain is proceeding according to a series of steps, according to some kind of a structure. In the case of the brain, there's some kind of a structure in the brain, and it goes step by step, as a computer does. You may have parallel processing, you may have different parts of the brain that are doing things simultaneously, but each one of them is essentially a kind of an algorithm, step by step. Now that's not obvious, actually, and I think it's wrong. I think there's actually no reason to suspect that that is the way the brain works, or the way the human mind works. That has a certain history, however. How this notion of the brain and the human mind as a kind of computational process, how that got in. What is certainly true is that if you learn formal logic, or you learn algorithms for computing things, compute the square root of 2 or something like that, you can learn to think step by step logically. So it's something the human brain can do, the human mind can do. The problem is, what about the reverse? Is that all the human mind can do? Or is that something you just learn? Is logic actually, so to speak, a natural way for the mind or the brain to function? I had a very funny discussion with a Chinese computer expert, older man, who I'm just encountered by accident. Actually, he's in California, involved in the big controversy about quantum computing. And I noticed his articles, which are on the Chinese internet, and there's a big polemic about this there. And his articles are filled, in the Chinese original, filled with just tremendous use of what I'll mention later, the Chengyu, the 4-letter metaphors, four character metaphors. So he was just saying, we were talking about different languages in science, because in the European tradition in the 19th century, actually you had scientific languages. German was a scientific language, French was, English was, Italian was, Russian was. Those were languages in which scientists wrote original works. And scientists generally knew 4 or 5 of these languages and communicated with each other in these languages. Well, you could say, well, why do you do that? Why didn't they just use English? Well, it's because languages develop different ways of expression. And you could actually talk about a German kind of school or way of thinking or way of communicating scientific conceptions, a French school, a Russian school, and they had their particular ways, you would say, kind of metaphors and ways not only of expressing things, but actually in a certain way of thinking, because we tend to think in a language, in a certain sense. So we were discussing, well, what about Chinese? And he said, oh, Chinese is a terrible language for science. And he was telling about the great problems of Chinese from his standpoint. Why? Because Chinese is so metaphorical. He said Chinese is great for poetry, but it's too ambiguous for technical science, let's put it that way. Has a tremendous ambiguity. Actually, Wilhelm von Humboldt talked about that also. He wrote about that, this characteristic of the Chinese language, which all human languages have, but it's driven and developed in a very specific direction in China. So now we could argue about that issue. It's a very interesting question about Chinese, how Chinese will develop in the future. But one very important point is that, and he agreed with this, but I felt that that was true, that in China, there was no tradition of formal logic. There was no Aristotle. Formal logic was never developed as a subject. So that, why do I say that? It's because we, most of us, say in the West, sort of assume that formal logic is something natural. I'm not against formal logic. I think it's very, very important to know what it is and to be able to think in a logical way. But that is not, let's say, the fundamental level of what the mind does. This is, I think, very important because in the development of what we call artificial intelligence now, it has a prehistory. It is also the form which we read about, which is used today all over the economy and in nearly every sector of human activity, or a lot that use computers. This form is not the only possible one. If you go back in the history of computers, there was something called analog computers, as opposed to, or put it this way, present day artificial intelligence systems are based on digital computers. Digital computers have a step-by-step algorithmic mode of operation. There was another approach to computing, which was called an analog computer. An analog, as the name would suggest, is a system which, in a sense, imitates, by its own characteristics, a process that you want to study, investigate, but not necessarily in a step-by-step way. It just does it. So there are, I like to use the case of protein folding. It's one of the very important area. A protein is coded. There's the part of molecular biology that looks like computer science. Genetics, molecular genetics, tells you that all the proteins in the body are coded into the DNA, the genes, that code the sequence of amino acids in a protein. And that sequence is read out, and you get a string when the DNA is the RNA and so on. You know, all this machinery you learn about. And the protein comes out first as a linear chain. And then something amazing happens, which is not programmed into the DNA. It's not programmed at all. The protein transforms itself from a chain into an extremely complicated three-dimensional structure. That's called folding, right? And that is not an algorithmic procedure. This is a physical process. It just does something and arrives at a specific kind of result. So I want to say this to emphasize that when we look at the universe, or processes that go on in cells, or go on in stars, or go on in an atom, there's absolutely no basis for thinking that these processes occur in some sort of algorithmic sense. For one thing, they're, as far as we can think, they are continuous. They involve continuous processes. So therefore, we live in an age where people think of everything as digital, tend to think of everything as digital. I'm saying all this because I'm going to get to some biology. I think it's important because what's called artificial intelligence in the history of it is very much linked up with a simplistic concept of how the brain works. And then when you have a simplistic concept of how the brain works, that can be then transformed into a simplistic concept about how the mind works. So that out of a simplistic conception of the brain came a simplistic conception of thinking. Okay. So now, there were really two approaches. There are two approaches to artificial intelligence. One called the symbolic one, and the other, I've forgotten the name of it, but the second one, which is associated with neural nets and so-called deep learning.
Right.
The symbolic artificial intelligence developed essentially out of the process of formalizing mathematical thinking, essentially formal logic, and the work of Hilbert and others, von Neumann, and a whole period at the beginning of the 20th century, actually goes back further, to formalize mathematical proofs, to be able to actually make machines that could, or computers that could check whether a mathematical proof is correct or not. That's a big step, because before that, in mathematics, a proof is something that convinces you. It doesn't have to be it doesn't have to be a sequence of strings of symbols which are derived each string from the preceding one by some rules, but rather something where a mathematician or somebody else says, yeah, that's a proof. But for various reasons, there was tremendous effort put into formalizing mathematics so that mathematical proofs could be reduced up to a certain point into such a formal procedure, logical deductive procedure. In a certain sense, Euclid's axioms, the tradition goes way back to ancient Greek times. But that symbolic AI came out of this idea that you do the same thing with thinking in general. That you take an area like, and I like to use this, machine translation, a fantastic technology, which is really amazing, but is in a certain sense also a Rosetta Stone for the progress and the fundamental problems of artificial intelligence. The part of this in the formalization of mathematics was the development of formal languages, and in which linguistic processes were associated with manipulation with these symbols or strings of symbols. And pioneers of this formal logic, particularly Alan Turing, John von Neumann, played a crucial role in the development of computers. And very early on, I know I don't have now the exact history in my mind, there came the idea that the human brain and its functioning operates in a combinatorial manner. I'll try to make that clear in a moment. But anyway, I'll get back. So symbolic artificial intelligence is the idea of formalizing some thinking procedure. You reduce it to steps. We could take a procedure such as, for example, translating. Noam Chomsky made his career, among other things, financed by the US military. There was great interest in the post-war period in developing machine translation to translate Russian texts into English. So linguistics got a tremendous boost from the US Department of Defense and other areas to try to get such computers to work. And that it stimulated very much a formal approach to linguistics. How do you take a sentence and break it up, analyze it up in such a way that you could translate that sentence by a set of rules from a dictionary in such a way that you'd actually get a readable, let's say, sentence from a Russian sentence to an English sentence. So what's going on here? In a certain sense, with artificial intelligence, mathematicians tried to conquer the world. We're living essentially in a near dictatorship of mathematicians. I say that in all, how should I say, realizing that I got a PhD in mathematics, I at least have a certain idea what it is. But most people are being controlled in some way by mathematicians without knowing what mathematics is. But if you're a good mathematician, you know that mathematics is something different from artificial intelligence. Anyway, so that was the beginning of this idea that when you're translating something, I'll take that as my example, that you have a mathematical function. It starts with a string of symbols, which is the Russian text, and you have a mathematical function that does something, and out of it you get a string of symbols, which is your English translation. So it's a function. You know, what mathematicians call a function. And what you want to do is to get an algorithmic procedure which will carry out that function. So there are two approaches. One is to use the analysis of the language, the grammar, vocabulary, to match up, it's a huge job, to match up the grammar of Russian with the grammar of English, and define all the steps, and really get a program that does that. This is a symbolic AI, symbolic artificial intelligence. There's another form, which I'm sure you're familiar with, which uses neural nets and is today in many ways the most successful and certainly dominates the machine translation area, called deep learning. The important to demystify deep learning, what it basically is, if you look at the work that went into it, is a method for curve fitting. You know, you have some kind of a curve, mathematician has some sort of a curve, and you try to have a method of developing a formula which will approximate the curve. Classical example, approximating a circle by polygons. And in all different kinds of areas, when we simulate a process by a computer, we're essentially curve fitting. When you simulate weather by a computer, you're taking a natural process and you're trying to approximate it by some mathematical function. What do you do in translation? Well, you have, in your curve fitting, you have to get some test points, some data points on the curve. So that would be, let's say, Russian sentences that have already been translated into English. Those are the points on the curve. You get as many of those as you can. Today, Google and these, they use all the translated texts from the United Nations, from the European Union, and now off the net by data mining all the texts where you have human translations, which they can pair up. And those are points on the curve, so to speak. And now you have a grand approximation process, which is a mathematical procedure, which is carried out by the computer to approximate that function. And the computer learns. The learning process is, we use the word learning, but we should be careful. That word was transferred from something which we know as human beings, or think we know something about, to what's really a very different process. It's a process mathematicians call of optimization. You have a measure for how close your mathematical function is to the real one. In other words, you test out, for example, your translation system that you've trained on a data set, and you put in a different sentence and see if it gets the right answer. And if it doesn't, you change it, and so on. So you have an optimization procedure. All mathematics, nothing else. And it doesn't depend, it has nothing to do with the structure of the languages. I could use that procedure to translate Swahili into Urdu without understanding anything, without understanding. I translate sentences without having any idea about the meaning of the sentences. Meaning plays no role. And in that sense, I like to say that artificial intelligence translation is useful cheating. I would cheat somebody into thinking I know Swahili and Urdu, but I'm translating using a procedure without knowing anything about either language, just correlations. Here we get to a little bit to the stupidity issue, right? How do you pass an examination without knowing anything about the subject that you're being examined on? This is very important because one of the turning points in the debate about artificial intelligence, actually in the linguistic part of it, was a controversy between Noam Chomsky and Skinner, the behavioral psychologist, about the nature of learning, about the nature of language. I don't want to go, this is another one of these big issues, one of the, but just to mention it, Skinner's model of learning was essentially a feedback process. reinforcement. Now, I assume you basically know what that means. You have your animal. The animal gets a stimulus and responds to it. And if the response is wrong, you give an electric shock. If it's right, you give a cookie or something, right? And somehow in the animal, there's an optimization process whereby its behavior becomes more and more close to what you want. What happens in deep learning, in artificial intelligence, is essentially that. And Noam Chomsky made a very, very excellent or very effective attack against Skinner on this notion of learning. But then he created a disaster, in my view, by moving from the optimization process or Skinnerian learning to essentially the symbolic AI formalism, to the idea that that language is basically a structure. It's a mathematical structure. Okay. Now I've gone far enough, I think, with this. I want to move a little bit now into 2 points about the brain and the mind. We have a kind of an idea how this artificial intelligence works. Same kind of thing with pattern recognition. The systems which identify faces or identify images, which is a big, like an automatic driving vehicle. It's supposed to identify whether what's in front of it is a car or a dog, or something other, has to identify objects. These systems are essentially trained in a similar way to what I talked about in translation. And I'll give you an example at the end of the problems associated with that. So, okay, I wanted to get to the brain, because I hope you get a sort of an idea of what I think the artificial intelligence is. It's just mathematics plus big computers, but mathematics which is developed in a very specific direction, or two actually different directions, by very clever and intelligent people who were also stupid sometimes. They're not contradictory. They're not contradictory aspects, very often coinciding in a certain way. So, what about the brain? How did it come that if you look at papers on so-called cognitive neuroscience, which is a huge field, which is benefiting from pipelines of money that are coming in, which is sort of the way that academic life works nowadays. You either have a pipeline, or you have a little tube which is keeping you alive. But there's a big pipeline going into the artificial intelligence and cognitive neuroscience areas. But if you look at the papers in this area, you will be struck with a language which is language of computers. You circuits, computation. Now I don't have the other ones here. Input, output, information. We use information so much nowadays that we forget that it comes from information theory. So what you find is that a terminology from computers applied to understanding of the brain, which is a bit strange, because that's sort of going backward, because actually the concepts came from study of the brain originally, neurons, into computers, but then stopped. What do I mean by that? There was a study, a lot of study about the functioning of the nerve system of the brain. Has a long history, it's very fascinating, and so on and so forth. But one of the early discoveries was the all or nothing principle, which we learned, we learned that, all of us, you have a neuron sitting there, it does nothing apparently, and then suddenly it sends an impulse out, so you're out. Action potential is called, right? A pulse of electricity. So from this standpoint, you have basically a 0 or 1. You have a digital, the neuron is supposedly a kind of a digital device. So you have a network of these neurons, which are on-off things where neurons are attached to each other through axons, and impulses come into a neuron from other neurons, and the neuron has, that's the input, and then you have an output. Something comes in, some patterns of impulses, and then the neuron will either make a pulse or not a pulse. I'm simplifying it all, right? And there were famous investigations of that, but so it happened that this notion of the neurons in the brain as digital elements, as on-off, as switches essentially, got itself inserted into the thinking about the brain, the nervous system, from early on. And although, and people involved in that, now I don't have the names, I don't have it on me. There were two biologists who, you'll turn up the names easily, who made, I think one is the name is McCulloch, and I'm sorry, I haven't got the name. There's a famous paper which plays a very big role in artificial intelligence, where two biologists who were at the same time very close to people working on formal logic tried to argue that neurons are essential formal logical elements, switching elements. Their view was a little bit actually more sophisticated than what then came out of it later. But it was part of this whole period where, of the development of computers, the formalization of mathematics, and the idea by von Neumann, Turing, and a whole group of other people, that with this way of thinking, with this approach, we could solve the problem of understanding how the human mind works, how the brain and the human mind work. These people were greatly overestimated, in my view, the power of their ideas and their methods, which is a characteristic of stupidity. I got that from the books on stupidity. One of the characteristics of stupidity is the tendency to overestimate the procedures and methods and ideas that seem to succeed, and to not be able to, what we call in American, think out of the box, not able to get out of your way of thinking and to say, does this make sense? Did what I just say make sense, or is it really nonsense? What am I doing here? What am I really doing here? What are you doing here? What did we just do? Was that nonsense? Was that bull? And so on. This capability of reflection, as opposed to the idea, we've got it. Our methods will work. Well, these people like von Neumann and Turing and so forth came out of the war period. They built a bomb. They built two bombs. They built the control systems. They had tremendous success in their mathematical methods. Very clever, brilliant people. But with this problem, I would assert, which has created a great deal of trouble. So the image or the idea of the brain as a network of these digital elements, in that sense, analogous to a digital computer, although the present digital computers don't work as networks, they simulate networks of artificial neurons. That's the deep learning approach, that you can get a computer to simulate an artificial notion of the way the brain would work if it followed this simplistic notion. That's a little bit of a mouthful that I've said. That's sort of expresses the way it works nowadays. Artificial neural networks, brilliant, fantastic tool for deep learning. It really is. It was taken from analysis of the visual cortex, of the first layers of the visual cortex, which do something very roughly along the lines of what these neural networks do. You can get to a certain point, you can get a kind of a correspondence. All right, but we go back, Turing and von Neumann and a number of the others basically wrote also, Turing very directly, von Neumann more cautiously, that neurons are, the brain is digital. It consists essentially of switching elements. Von Neumann was a little bit, he knew some biologists. I mean, at that time, it was clear enough, I believe, for anyone who's interested in biology, who's looking at the biology or the biophysics, that this couldn't be right. They essentially went off on this direction. And this is part of the reason why people grow up in this cultural atmosphere, the ambiance that we have, with the idea that it's well established that the brain is a digital system. But if we look at the, and there are dogmas associated with that, and it's very, very useful to compare those dogmas with what we know today. And that's one point which is also very good in biology today, with all the problems of biology and limitations. The technology of actually observing neurons, for example, has developed so much that you can really say this is complete nonsense from A to Z, this model of a neuron as a digital element. So I want to go through the 5 very quickly. I'm coming to the end. Things that are or were until relatively recently taken for granted. One is the idea that the brain is hardwired. You have the neurons, you have their axons where they contact each other, and you have a network. For a long time, it was believed, it's well known, obviously, that when you have an embryo that develops out of a single cell, obviously the neurons had to get there in this embryogenic process, development of tissue differentiation and so forth. So the connections were not always there. The neurons were not always there, and the connections were not always there. But the assumption was that after a certain age, all the connections are there. And so you have a hardwired brain, with the axons being the electrical wires to conduct the impulses. Well, it's now known, very well known, that that's not true. You have so-called neuroplasticity, that new axons are being formed all the time in the brain. And the synapses, where the neurons contact each other, are constantly changing, reforming, changing their characteristics, and so on and so forth. So synaptogenesis, new synapses formed, and so forth. And it's now known that this plasticity, which does not exist in computers, which are really hardwired, can only be superimposed, is essential to the functions of the human brain, or actually the brains of practically all animals. Second, in the adult brain, neurons only die. At a certain point, you have so and so many neurons, and then you lose them as they, get old. But neurons never grow back. Wrong. We now know that at least in some parts of the brain, neurons are actually born, and not only that, new ones. but they actually migrate like amoebas through the neurotissue and find another place and then sprout axons. Now, okay, third dogma, neurons operate in an all or nothing fashion by the generation of these action potentials pulses. No, it's been discovered that the neurons have a membrane which is electrically charged, and this membrane has membrane oscillations, waves, charge waves, which are propagated and generated, and they actually propagate beyond a single neuron into the surrounding tissue, and they affect the way the neurons fire. So you could say there's a kind of a field, a little bit like the de Broglie's guiding field. You have a electromagnetic environment which affects the apparently digital processes in the brain. So, therefore, also we know that the neurons communicate, if we want to use that word, they interact, not only through their electrical impulses, but by a vast variety of chemical substances. Last dogma, the idea that the brain is based on the neurons. Now we know that the glial cells, which were supposed to just be there to hold the neurons in place and to insulate the axons, like electrical wires that are insulated, that they are intimately involved in the processes of the brain. They are at least half of the cells in the brain. I think it's actually 2/3. Only 1/3 are neurons, and the other 2/3 are glial cells. So now it's sometimes called the other brain. So suddenly we discovered another brain. So the picture of how actually the brain is totally different. It's changed totally. But people are still marching forward, stupidly, with this image of the brain in their mind, and applying these worn out metaphors, you might say, to trying to understand the mind. So now let me get, at the end of this, to the last point, namely the mind. You might say, well, why didn't I start with that? Well, because sometimes it's good, I think, to sort of clear the air with things that are really, in a certain sense, scientific hard facts. I mean, there are no real hard facts in science, but there are things that are pretty well established, let's put it that way, which already clear the air from certain things. We were talking about the brain as a substrate, part of the substrate of the mind, you might say, that we don't have. Well, I'll put it another way. Some people say, well, yeah, the human mind is based on the brain. The brain is a physical system. Therefore, the human brain satisfies the law or follows the laws of physics, right? You write down the laws, the equations. Therefore, the mind, which seems to be in what we call, mathematicians call, a one-to-one correspondence with the brain, also functions according to mathematical laws. There's a little problem with that. And that is, we assume that we know the laws of physics, all of them. How do we know that? You assume we know everything about physically, about how the mind functions. How do you know that? We don't know that. Who has modeled the brain, the whole brain? Who has modeled a single cell? Who has modeled a single protein as it actually is? So I think, that's my own way of thinking of it, that if you attempt to understand or to model the mind, however, on the brain, the functioning of the brain, with physics, there'll always be something left out. That's the way science works. There's always something left out. We know from science, the more you look at the universe, the closer you look, the more you find. Okay, we get to the mind now, and I want to take language as a good example. Because the human mind is obviously a very big, a very big subject. But to make it concrete, we take translations. What is human language really about, or what's the problem of translation? A good human translator looks at translation from the standpoint, I have a text or somebody talking. I first want to understand, what are they trying to say? What is the meaning of what they're saying? No. Then when I've got that, I then go to work and try to say it more or less, try to say the same thing in the language I'm translating into, more or less with the words or the form of expression that the person used. I don't want to violate necessarily the way of speaking, because that's also part of what's communicated in a certain way. So what the artificial intelligence system does, as I indicated before, has nothing to do with that at all. There's no, the concept of meaning plays no role. And here we get to a second aspect of stupidity, which I also got from the books. The books that I studied were books, not philosophical books, but it's very often very useful, actually, to read books written by, what do you call them, management consultants. Because sometimes in business, there's a more rigorous criterion than there is for people just sort of sitting in offices, universities, thinking about things. I'm not against universities by all means, but sometimes you get actually better readings from people who are actually dealing with stupidity as part of their work. Now, what do I mean by that? You have a wonderful company with intelligent, talented people, good leadership, and it goes bankrupt. Why? What happened? It had everything going for it. So the management consultants go in, and some of them, a couple of books that I read, try to understand this, and in this context develop the notion of systemic stupidity. It's not quite the same thing as the stupidity of when we say just by ourselves, oh, I made a stupid mistake, or I was stupid about this. That's a little bit different, but anyway, that's not my subject here. But one of the characteristics of stupidity is the inability to understand what another person or another situation actually means. When you say, this person is too stupid to understand, it correlates with the other problem, that not able to understand because they are living in a system, which they believe functions, and they cannot perceive or take in something which is outside that system, which is an anomaly, let's say, from a standpoint of their concepts. Okay, we get to the translation issue. Now we have a very interesting additional point. What is language? Is language communication? Is language, the people who developed artificial intelligence and who were involved in it very deeply in the early period, were very much influenced by information theory and cryptography. Alan Turing was a genius of decoding the famous British intelligence successes. As far as I have read, they were quite successful in actually finding ways to decode the German codes, military codes. And that's a big area. It's actually a big area today also, cryptography. So out of this developed the idea that that language is a communication of information of the sort, essentially, that you have in military, the coordinates, and now attack there and do this and that. Is that what human language is? Well, we do sometimes communicate orders and numbers, but maybe human language is something very different. If I have a bird that's singing and I say, well, is this communication? Some biologists will say, yeah, well, the birds are communicating information to each other, but maybe they're also being happy. Why is it always communicating some kind of signal? So imposed upon a way of looking at a biological process or a human process is a grid of concepts which come out of codes, formal systems, and so forth, which constrain and make stupid the people who are not able to see the limitations of these concepts, and not able to see that they're imposing upon something a mindset which is not intrinsic to the subject. Of course, you always do that to a certain extent. We can't avoid bringing with us our brain or whatever is in it into any subject, but there's a little difference in the awareness or the ability to become aware of what we bring into a situation, of our own mental process. So there are these, so if we look at language and say, what's the function of language? Is it to communicate information? Well, I would make a qualification. First, I think that's completely wrong. That's one of the things that language can do. But I would say that human language is characterized, human languages as opposed to, let's say, formal languages in mathematics, by irony, humor, and metaphor. One could go on with that, but those are three things that are very crucial to the problem of translation. In other words, what is irony? Is irony the communication of information? Is humor the communication of information? Humor is a way that we get something to happen, hopefully, in another person or an audience, or to make them happy, not by communicating information. So somebody say, well, that's irrelevant to the problem of translation. Wow. I think not. This is very, very important, because it can make the difference between great historical events. You read Heine, for example, the irony in his poems, which were part of the reason why his poems were revolutionary and moved populations to make revolutions or attempted revolutions. So from this standpoint, then we get from that to the issue of ambiguity. And this is a little bit of a side point, but a lot of the discussion about artificial intelligence and the cultural history of artificial intelligence is bound up with the Vienna Circle, the philosophical Vienna Circle of the 1920s. Actually, it goes back a little bit further. I can't remember when it started, which was essentially a very left-wing movement. I think nearly all of them were socialists, but in a very specific sense of socialism. Part of the idea was to clean away the vestiges of, you might say, classical culture from language, to develop a universal language which is 100% precise, and and would then unite humanity. And you would have a new society and a new man. Those are kinds of ideas that were around at that time. Also because of the left-wing people wanted to get rid of religion and wanted to clean that all away, right? And they used science in the sense of science is the way to get out of all that. And have a real rational. It was a bit of sort of the model of, the Soviet model of the idea of the new society, the scientific society. So out of this Vienna circle came also the idea, and I think Neurath was the name of him, actually did try to play with the idea of universal languages, where the ambiguity is completely removed. There's no ambiguity. If there's no ambiguity, you can't really use irony. You don't have metaphor. You don't really have humor, because humor depends on the play of different meanings. So if you only have one meaning, one-to-one functions, we say in mathematics, you don't really have metaphor. So that's, again, only one little part of the issue, and it's very interesting to play with that, as I've done, to take Google machine translation programs or that you get on the internet and plug in some metaphorical expressions and see what they do with them. And then you begin to actually you have a little bit of a problem, because even a bad translation of many metaphors in the other language, the mind works in such a way that it can get something metaphorical out of it, even if it's in a different language. Anyway, it's a revealing and interesting way to see the limitations of the problem, the stupidity of artificial intelligence, revealing that it does not understand the text that it's translating. And the wonderful cleverness of the programmers that can accomplish that, how to translate texts, more or less, often very useful way, without anything that corresponds to meaning. So the last point is this issue of meaning, because, as I said, in artificial intelligence, one of the things that's missing, which is essential to the human mind, is meaning. You say, well, what is meaning? That's very hard to define, because if you say, what do I mean by meaning? You've got a circular meaning. Meaning is what I would call an inherent characteristic of the mind, and very close to maybe the deepest levels of the mind, or it's presupposed by everything else. Now, this gets me now to Gödel, and a very interesting point. This is a whole other presentation, very, very, very deep thing. Namely, the question, could you build a computer that could solve all mathematical problems? You have very simple mathematical problems, simple in the sense that you can state them very simply. For example, is every even number a sum of two prime numbers? I think it's called the Goldbach conjecture. Now I've forgotten it. See, I'm an aged mathematician that hasn't been doing mathematics for a long time. That's one of them. There's another so-called Fermat. Very simple, simply stated questions about whole numbers. Right? You know, the 8 is the sum of 3 and 5. 10 is the sum of 5 and 5. Right? And 82 is the sum of 11 and 71. Anyway, you could try it. And I think if you go out to very even numbers up into the billions and trillions, you always find that they can be expressed in at least one way as a sum of two primes. But no mathematician has found a proof of that. Maybe it's not true, maybe in a trillion, somewhere out there, there'll be a number that is not the sum of two prime numbers. So now is the question, can we get a computer that will be able to give us a yes or no answer for all such problems? Well, Gödel proved that there is no such computer program. In fact, a Russian named Matyasevich, in developing these ideas much further, could basically say, well, if you give me a computer program or an artificial intelligence system, I can invent a so-called Diophantine equation, an equation involving whole numbers. It's a number theoretical problem, such that the computer will give the wrong answer. So now Gödel makes another move which people didn't, a very interesting, very important point, which is that it turns out that there's no way in mathematics to formalize or to uniquely describe what we call the system of whole numbers, 1, 2, 3, 4, 5. What do I mean by that? Well, we have Euclid's axioms, right? Where there are axioms for geometry, for simple geometry, like through 2 points, there is exactly one straight line, right? And then there are a set of, I don't know how many it is, 5, maybe more axioms. And from those axioms, you can prove basically all of the true statements about figures in plane figures in ordinary geometry. And there's a system of axioms for arithmetic called the piano axioms. And many statements about the whole numbers can be proven on the basis of these axioms. So now comes the question, can you prove or can you decide on the basis of those axioms any question that you could pose about the whole numbers? Or another very interesting question, could you find a system of objects, for example, the ordinary numbers plus some extra numbers, which satisfies, for example, infinite numbers, add just some symbols, alpha, beta, gamma, in addition to 1, 2, 3, and define the addition and so forth. You create a system that is completely different from the ordinary numbers, has some infinite numbers, but actually satisfies the axioms, the piano axioms. In other words, your system to try to formalize an area, a concept, like a concept of a whole number. What is a whole number? Well, a whole number is something that has this and this and this properties. It turns out that there will always be systems of objects which satisfy the same axioms, but are completely different. For example, so-called non-standard models of arithmetic, which are systems of mathematical objects. They satisfy the same set of axioms, same properties as ordinary integers, but are very different. In other words, we can't characterize them without ambiguity. Any set of axioms is ambiguous. For example, we cannot define what we mean by a finite procedure, something that ends at some point. Cannot. So therefore, to proceed, even in this very limited domain of mathematics, it turns out we have to look more carefully at the concepts. What does it mean, the word finite? What does whole number actually mean? And Gödel and others came to the conclusion, Gödel particularly, came to the conclusion that even these very simple concepts are actually what's the German word called unerschöpflich. You can never come to the end of explicating them. It's like the notion of meaning. You can't sort of put it in a box and say, meaning is X, Y, Z. The minute you do that, you don't really have meaning. Therefore, the procedure or the method of essential to the progress, even of this limited domain of mathematics, is the ability to move forward in clarification of meaning. So meaning is at the center. There is nothing in artificial intelligence that has any correspondence with that. And therefore, to the extent human beings are no longer aware of these characteristics, to the extent that human beings model their language on the notion of communication of information, signals, computation, their attention is directed away from irony, humor, metaphor, meaning. And in that sense, people become stupid. Well, they become imitations of artificial intelligence. It actually should be the other way around. Artificial intelligence is an attempt to imitate certain useful capabilities of the human mind, just as a crane or other mechanical device imitates useful abilities of the human musculature. In those specialized areas, they're much more powerful than the human musculature. So what's new? So artificial intelligence and computers are much more powerful at doing certain things than the human mind is. We would get bored to do all those computations, right? So that's basically what I had in mind. Now I've taken more time than I originally wanted to, but I hope it was interesting, and I hope there's some time to discuss. And thanks for your patience.
No, thank you so much, Jonathan. That was really glorious. And this is something that I'm going to be recommending that everybody that I've ever met watches this and rewatches this, because there's so much to unpack. And really the underlying theme, which is more than the sum of all of the parts you brought together, is really very interesting. Already we have a nice little queue forming. So we have John, Bob, Anton, and a thought from Peter so far, and I'm sure that more questions are going to pop up as we proceed. I myself have some questions, and I'll save that towards the end. But John, you were the first in queue, so what's your thought?